Ja, meine sehr verehrten Damen und Herren, liebe Mitglieder des Vorstandes der IBINA, liebe Mitglieder der IBINA, meine sehr verehrten Damen und Herren, die Sie dieses Video von zu Hause aus ansehen. Herzlich willkommen zur diesjährigen Preisverleihung des IBINA-Preises unter ganz besonderen Bedingungen, anders als wir das sonst gewohnt sind. Erlauben Sie aber auch, dass ich, und das sollte bei einem Wissenschaftspreis durchaus legitim sein, für den weiteren Text ins Englische wechsle, denn die Preisträgerin ist nicht nur englischsprachig, es scheint mir angemessen, die Preisträgerin in ihrer Sprache zu adressieren. Making a speech in honor of the winner of Marburger's competition for bio and nanotechnology is usually a very formal and festive event. In any other years, we would be gathering in the historical town hall in a solemn atmosphere. We would take the most beautiful room we have, and we only use it for most important moments. We would have invited at least 50 guests, so it seems strange to me to record my speech as a video address. Clearly, technology and the virtual world have arrived. Corona gave it to us. But digitally or in real life, holding this speech is a great honor. Honoring people for their specific commitment, for their life's work, and awarding them for their outstanding successes is a wonderful task, even if I'm only speaking to a camera. It is therefore a particular pleasure for me to honor the winner of Marburger's Prize for Bio and Nanotechnology 2020, Dr. Miller. I would like to extend a special welcome to you. The Biology and Nanotechnology Initiative, IBINA, is honoring young scientists for the 7th time. The Marburger Prize for Bio and Nanotechnology has thus already become a small tradition. Its importance reaches far beyond Marburg. Since 2014, this prize has been awarded to young researchers who have not only produced outstanding scientific achievements, but also have shown that their findings are highly economically relevant. That in itself makes this prize very special. It is important in Marburg and it is important for the entire region. Marburg doesn't have a university. Marburg is a university. It is a center of knowledge and research, the natural sciences, medical and health sciences, which are being researched with outstanding success at our university, and at many research institutes are a major strength of our location. With a large number of companies, some of them world market leaders in their fields, Marburg as a science and business location is of great importance nationally and internationally. We are proud of that. As a city, it is important to us to support young scientists. It was this idea that launched the Initiative for Biotechnology and Nanotechnology, the IBINA. The IBINA is supported by renowned scientists from the region as well as by many companies from the sector of biotechnology, nanotechnology and pharmacy, alongside numerous other supporters and the university town of Marburg. That Marburg is a specific center has been shown in national and international recognition in the last weeks as BioNTech, one of the first producers of a specific COVID-19 vaccine, has chosen Marburg as its site, and I can only support this was a brilliant decision and not a coincidence, but a result of systematic build-up of competence as well as successful innovations and startups in our city and in our region. The aim of IBINA is to translate high-quality research results into economic success, and thus to bring up the regional center Marburg forward in a supra-regional competition. With various offers for the networking of science, business and young researchers, and of course also with today's funding award, the city wants to create an innovative climate in which good ideas can mature. But it's more than that. We want young researchers to feel so comfortable that they remain loyal to the city and the region even after they have completed their studies. The application phase for this award began last year and we received many excellent submissions. It was a hard decision, but one researcher made the race. Dr. Miller, you were able to convince the selection committee with your really outstanding work. You have done excellent research on the design of novel catalytic systems for the use in biotechnology and chemistry. With the new nanotechnology, the so-called microfluids, you have succeeded in inserting complex biocascades in an artificial cell envelope. Thus, an artificial chloroplast was created that converts the greenhouse gas carbon dioxide more efficiently and faster than in the natural process with the help of light. Dr. Miller, your work is not only technology, a milestone for synthetic biology. In other words, your ability to reconstruct complex lifelike processes, but also enables concrete applications such as the sustainable biosynthesis of raw materials from carbon dioxide. And let me put it like this. This research really is at the top of time today. Facing the climate crisis and working on one of the greatest challenges to mankind, you have shown us that science is able to work, to help, to support, to create new ideas in circumstances one would not have thought about in advance. As a first-time author, you were able to publish the result of your work in 2020 in Science, which is not a thing too common even among outstanding scientists in our area. So I'm looking forward to hearing from you about the secrets of your successes in research and the possible applications of your research. But before I hand over to you, Dr. Miller, you should receive our highly deserved honor. Due to the specific conditions of this pandemic, we have decided to hand over our prize symbolically. We will hand over the prize in person with strict physical distancing and hygiene at a later stage.
Guten Abend, meine Damen und Herren. Ich bin Taryn Miller, ein Postdoc am Max-Planck-Institut für terrestrische Mikrobiologie. Ich bin der Initiative Biotechnologie und Nanotechnologie, der Stadt, der Universität und natürlich dem Komitee sehr dankbar für diese Auszeichnung. Die letzten 5 Jahre, in denen ich die Gelegenheit hatte, in Marburg zu arbeiten, waren ein unglaubliches und bereicherndes Erlebnis. Schon seit Jahrhunderten wurde in Marburg die Wissenschaft groß geschrieben. Nicht wenige Entdeckungen und Erfindungen, die sowohl Forschung als auch Industrie voranbrachten, hatten ihren Ursprung in dieser Stadt. Die Wissenschaft in Marburg trägt dazu bei, das Leben auf der ganzen Welt zu verbessern, etwa durch Innovationen und Initiativen wie die Initiative Biotechnologie und Nanotechnologie, was die Weiterentwicklung dieser wunderbaren wissenschaftlichen Forschungsgemeinde fordert. Ich bin sehr geehrt, diesen Preis für meine Arbeit zu erhalten. Ich möchte hiermit die Arbeit, die ich natürlich zusammen mit unserem internationalen Team in Marburg vollbracht habe, vorstellen und werde deshalb auf Englisch weitersprechen. Humanity is continually inspired by the natural world and has found ways to use what nature has already learned to do as inspiration to innovate and to create solutions to humanity's pressing issues. Like a bird wing has inspired a plane, or how whale fins have inspired turbines. When solving such issues as climate change or the need to create a more sustainable bioeconomy, we can also look to nature for inspiration. Nature has found ways to close the carbon cycle, and scientists and society can use this as inspiration. We can look to plants, algae, and cyanobacteria, which naturally convert the greenhouse gas, carbon dioxide, into biomass and using light as fuel. Our goal was to build similar systems, and we sought to mimic natural photosynthesis, systems that use light and turn carbon dioxide into chemicals. Chemicals like fuels, food, medicine, and building materials. Natural photosynthesis is organized into nanoreactors that are inside plants or algae. This is the chloroplast. This nanocompartment houses membranes that have molecular machines necessary to convert light energy into chemical energy. This fuel powers biochemical pathways that generate organic chemicals that life depends upon. We asked, can we rebuild a similar or even yet a better system? We sought to create an artificial chloroplast. If you take the example of a wing, you don't just learn how to fly, but by building a plane, you learn how to improve flight, and you can make it faster and build an eventually better plane. So by mimicking life systems, you can learn how to improve these processes. You use nature as inspiration to build new solutions and to continue to improve these solutions. However, to use nature's solution for carbon dioxide and bioconversion as inspiration, we need specific tools and technology. To build an artificial chloroplast that mimics natural photosynthesis, you need to create a biotechnological solution to fix CO2 in a cell-sized compartment. For this, we use synthetic biology, which is a biotechnology that uses natural parts in new combinations. You also need nanotechnology, specifically microfluidics, which is a way of manipulating liquid at the nanoliter scale. And you need to bring both of these tools together in a useful way. If we discuss first synthetic biology, we need to capture CO2 as good or better than nature. Nature invented several solutions for carbon fixation. However, with our understanding of nature and biochemistry, we synthetic biologists can expand the possibilities and combine enzymes in new ways, and can expand the reaction space for CO2 fixation, creating novel solutions for CO2 fixation that's new to nature. These solutions actually go beyond nature and create radically new pathways not invented by nature, but built from nature's parts. Our team in Marburg designs theoretical pathways and builds them from molecular parts or enzymes to create novel CO2 converting pathways. And we seek to implement these new solutions into natural and synthetic cells. But how do we design fast and efficient carbon fixation? Our lab designed many synthetic CO2 fixing pathways that do not exist in nature. These look complicated, but they all share something in common. They all fix CO2 that will produce organic chemicals that can serve as the basic building blocks for other metabolism or the production of other valuable chemicals. These pathways expand the possible space for CO2 fixation. Starting with one of these designs, one of my colleagues took one of these pathways, he optimized it and realized it in vitro. But first, this theoretical pathway needed to meet specific criteria. It needed to be fast, or in chemical terms, it needed to be kinetically favorable, so that carboxylation reactions were efficient and better than the carboxylases found in plants. The pathway needed to be energy efficient, or thermodynamically favored, so that a low amount of energy was required to work. My colleague Thomas Schwander established this in the lab, and he made the parts work together through building complexity. This allowed all of the parts to operate simultaneously, which was a very difficult task because all of these parts come from many different sources. The catch cycle ended up being built from 15 different enzymes that come from 6 different organisms. They are taken from all domains of life, including humans, plants, and bacteria like E. coli. With one of the reactions, we could not find a suitable enzyme, and therefore my colleague needed to take that enzyme and engineer it to have a new function. It is really amazing that these enzymes can operate together and fix CO2 because we collected them from many different sources, and we bring them together in a new combination. However, how do we power this cycle? Specifically, the cycle needs chemical currency in the form of ATP and NADPH. Natural photosynthesis will generate NADPH and ATP by converting the energy harvested from light. For this, we isolated the nanocompartment from plants, from spinach specifically, and used this as the powerhouse of our artificial photosynthetic system. Inside the chloroplast, which is a natural internal cellular compartment, are membrane systems called thylakoids. They house the enzymes and molecular machines necessary to harness the power from the sun and create the chemical currency needed to power CO2 fixation. We wanted to use these to convert light energy into chemical energy required to power the catch cycle, hopefully creating an artificial photosynthetic system that converts CO2 into organic compounds. So can you power the catch cycle using thylakoids? Initially, no, we could not. This required the optimization of the function of each component. The catch cycle and the thylakoids needed to be able to operate together. Eventually, however, after this optimization, we were able to power the catch cycle and produce the inorganic molecule from inorganic CO2 using light as power. If you keep the reaction in the dark, nothing will be produced. This organic molecule can be used by a cell or other enzymes to make useful biochemicals such as antibiotics or fuel. However, we were not finished yet. We wanted to build more complexity to learn about life and build a tool for high throughput analysis of the system. You can see that the chloroplast is highly organized in time and space, and the thylakoids and the CO2 fixing enzymes exist inside this additional compartment. Therefore, to further mimic this lifelike system, you need to put both the catch cycle and the thylakoids within another compartment. And this will mimic a chloroplast that is capable of using light to drive CO2 fixation. So in order to structure these things in time and space, we needed the second technology, the nanotechnology called microfluidics. We did this in collaboration with Jean-Christophe Barret's group at the University of Bordeaux. Using this nanotechnology, we create a compartment that has the thylakoids and the catch, allowing the artificial chloroplast to be created. With microfluidics, we were able to encapsulate each of these parts. This will occur at a microscopic scale and will create water and oil droplets. An oil phase will pinch off small amounts of a reaction mixture that contains each of these components into a cell-sized droplet. These droplets will contain the reaction components, and they'll exist in a sleeping state until they're illuminated. The droplets can be loaded with individual reactions or reaction networks, allowing flexibility in the system. Each droplet is an independent microreactor that contains a power-generating module, the thylakoids, and enzymes capable of performing biochemical reactions. These are cell-sized, catalytically active nanoreactors that we can program with many different pathways or variations of a pathway, and we monitor the NADPH fluorescence to assess the performance of these droplets. This automated miniaturization allows for analysis in real time and comparisons of differently programmed reactors side by side. You can see in this video that the two populations of droplets react differently. When the light is on, the NADPH will go up. The speed that it increases is dependent upon the thylakoids that were added. when the light is turned off, the NADPH will be consumed, and this will occur at a rate dependent on the enzyme concentration. Within these compartments, we mimic life. The reactions that occur in the compartment are separated from the environment around it. These compartments are independent and can allow for the multiplexing of experiments side by side. We can equip these droplets with the catch cycle and create an artificial chloroplast that fixes carbon dioxide using light, forming an organic molecule within the droplets that have been exposed to light. This new invention serves as a novel source of innovation because we can learn so much about the reactions occurring within these droplets in a high throughput fashion. In the long term, catalytically active microreactors or artificial cells could be created that could replace classic processes in biotechnology and test or enable new sustainable CO2 neutral synthesis processes on a small scale. In our lab, we're already working on using this organic molecule that we generate from carbon dioxide to produce other valuable products like terpenes that can be used as scents or fuels. We've also added additional modules that allow us to produce antibiotics directly from CO2. This system created the most integrated combination of a synthetic pathway with natural parts, and the technology developed can pave the way to high throughput improvement of synthetic cycles and allows us to use light to produce new and interesting chemicals. And ultimately, we created a compartment capable of generating organic compounds only using solar energy. This can be used as the building blocks for other useful compounds, like medicines or fuel. And eventually, the cell extracts could even be replaced in the system and powered by electricity. So if you go back to the wing analogy, the goal of this work is to gain understanding through building synthetic photosynthesis. That is, that we don't just learn how to fly, but we can build a plane that can fly across the ocean. So that by building a system that mimics life, we can learn to build better systems. Systems that allow us to address some of the world's most pressing issues. We can improve photosynthesis and eventually efficiently convert CO2 into valuable chemicals. It is important to note this would not be possible without basic biology and physics. And as Max Planck said, insight must precede application. This is what makes Marburg such a wonderful place to do research. That here, basic biology can lead to innovative and life-changing inventions. Here we have the freedom to explore new ideas, both in furthering our understanding of basic science, but also in the applications of that science. With this, I would like to again express my gratitude for my time in Marburg. I'm grateful that here I was afforded the freedom to explore new ideas and that my colleagues and scientific community continue to challenge me and my work. I would like to thank the people involved in this work, including my collaborators, the members of my lab, my professor, Dr. Tobias Erb, for giving me this opportunity. Again, I would like to thank the members of the Biotechnology and Nanotechnologie Initiative for giving me this honor and continuing to build up and support the scientific community here in Marburg. Vielen Dank.
Ladies and gentlemen, I would like to thank some people who made this award possible. The annual award would be unthinkable without the commitment of a competent and decisive jury, which always comes to an informed decision. Thank you all. Thank you to all the members of the selection committee for your contribution, for your work, for the hours you spent on deciding on this award. I would also like to thank the company Seidel, who once again donated the prize for our prize winner this year. And I would like to thank all those from the City Department on Business and Economic Development who did a lot of work in preparing and organizing the prize, the ceremony, and the IBINA initiative in all. And thanks to Mello for the production of this movie. Before we finish the ceremony, I would also like to tell you about the new competition in 2012. 2021. Applications are open until 30th of June. Und das sage ich auch gleich nochmal auf Deutsch. Bewerbungen können bis zum 30. Juni eingereicht werden. IBINA will be actively promoting the call for application in the coming months. And the further information as well as the application forms can be found on the IBINA website. Die IBINA wird in den nächsten Monaten die Ausschreibung breit publizieren und die Bewerbungsunterlagen finden sich auf der Website von IBINA. We would also very much appreciate all of you helping us spread the word about the new competition, which we are very looking forward. We would also appreciate all of you helping us to spread the word about the new competition, which we are looking forward to very much. Of course, we hope that the 21 Prize Award can be awarded in the usual ceremonial setting, and we again will be able to see all of you in person and not on video. Thank you very much for watching and stay safe.